Okay, so I guess if you've come to a talk about WebAssembly, I guess you've heard some of the hype about it. And it's supposed to be this revolutionary new way to do web programming, so you can program your web pages in languages other than JavaScript. And some people have even gone so far as to say, this is the future of cloud programming. And I guess I just wanted to take a look at whether that's true or not. So the thing is, as Java programmers, we've heard a lot of the same stuff before. So if you look at, the things about the advantages of WebAssembly and how a WebAssembly system is supposed to work. If you look at Java, like the idea is if you're programming Java, you start with your Java code, you stuff it into a Java compiler, it outputs bytecode, and then you can run that bytecode on a bunch of different virtual machines running on different machine architectures. And then they say, okay, this Java way of programming is great because you can write your code once and run it anywhere on all sorts of different machine architectures. It's secure and it's mostly fast, I guess. And the thing is, but when you look at WebAssembly, it's sort of the same. So you have a bunch of languages that you stuff into some sort of compiler, and these compilers will output WebAssembly. And then you can run this WebAssembly on a bunch of different virtual machines running different machine architectures. And some of these virtual machines might even be running in a browser. And they say, okay, the advantages of WebAssembly are it's polyglot, so you can program in different languages. But in a way, Java, you can also do that, right? Because you can write Scala or Kotlin or whatever. And it's portable, which is the same as write once, run anywhere. It's secure, and it's fast. And yeah, so basically, just from these general overview things, it looks like the main advantage of WebAssembly is just that it runs in a browser, and which Java used to in the past. And if the main advantage is just that it runs in a browser, why are people proposing using WebAssembly in the cloud? So I guess what I want to do during the rest of the talk is to look at, is WebAssembly better than Java? And if there are ways in which it's better than Java, then how can we sort of make use of WebAssembly with Java so we can take advantage of what these features are? Okay, so I'll talk a bit during the talk about what WebAssembly is. Then I'll talk about different ways of mixing WebAssembly and Java. So I'll talk about using WebAssembly from Java, and then I'll talk about compiling Java to WebAssembly. Okay, so as I mentioned before, Java and WebAssembly, if you look at the bytecode and WebAssembly part, they're conceptually the same, right? They're some sort of low-level code that you can feed into different virtual machines and run them on different machines and different architectures. So I guess, let's look at what makes WebAssembly different from Java bytecode. So, like bytecode, WebAssembly is a low-level language. So it's a sort of assembly language. It's a little bit different in that it's a structured programming language. So like something like Pascal or C or whatever, everything is broken down into functions, and then those functions are broken into if blocks and looping blocks. So there's no go-tos in WebAssembly, which is a little bit weird for a low-level language because like bytecode has go-tos and stuff like that too. So it runs in a virtual machine like bytecode, and it's all sandboxed to give you security. And I guess the main difference between WebAssembly and Java is that WebAssembly was designed for running C and C++ code. So I guess when they designed WebAssembly, the idea was they wanted to, I guess JavaScript was too slow, so they wanted to find ways to get all these C++ libraries for doing image processing and all these C++ games and getting that running in a browser somehow and doing it safely. And so they went with WebAssembly for that. So just to give you an idea of sort of the core WebAssembly virtual machine parts. So in a WebAssembly virtual machine for core WebAssembly is just single-threaded. So that's the same. It's like your machine only has a single core, or a single CPU. And this CPU is little endian and 32-bit. So you can access up to 4 gigabytes of memory. And you have like a 4 gigabyte linear address space that you can access. You have your program code. So your program code is divided into functions, and all these functions have type signatures. So whenever you call a function, you have to match the type signatures. And then you have a stack. If you have functions, you need a stack for storing the return pointers and all your local variables for calling all those functions. But because WebAssembly is for C++, sometimes for the variables you have on their stack, you get memory references to them or pointers to them and pass those pointers around. So you need a separate stack for storing your C++ local variables that you get memory references to. And then WebAssembly is only for computation. So if you want to do any sort of I/O or user interaction, you can't do it from WebAssembly. So you have to import JavaScript functions that you can call out to from WebAssembly. And then, whatever you import, you can call out to you. And then similarly, you can export some of your functions so that JavaScript can call into your WebAssembly code. So this is the sort of core WebAssembly model. But in fact, there's a lot of variants and extensions to WebAssembly. Like I've only shown a small subset here. And basically, all of these extensions, they add new instructions to WebAssembly. And it's a bit of a mess of who supports what. And there's no real feature sniffing or anything like that. And you have to recompile your code to incorporate all these extra instructions. So basically, the main idea is you just choose a target and hope everyone supports it or not. And it gets a little messier than that because things like garbage collection and multi-threading, I guess JavaScript is single-threaded. So their garbage collector by default is single-threaded. So you can have a WebAssembly VM that supports garbage collection and multi-threading, but maybe not both, and weird things like that. OK, so that's the WebAssembly model. And like I said, because with WebAssembly, you can run C++ code on different machines. But being able to portably run C++ code is not that interesting because C++ is already a sort of portable language. So being able to run in different machine architectures, it's not that technically interesting. What is interesting is that WebAssembly lets you run the C++ code safely in a browser, right? Because when you run things in a browser, you're downloading all sorts of who knows what off the web. And you can't trust this code to not hose out your system. So WebAssembly has a sandbox to protect you from that. And I guess I'll now look at what are the limits of this safety that the sandbox provides. So to understand the sandbox, it's useful to look at just what happens if you run some C++ code unsandboxed, so just in a regular process. And I guess in a regular process, you have your memory, where everything is located. Your program code exists in memory. And then you have your stack that exists in memory as well. And then you have your CPU with your instruction pointers and registers and stuff like that. So if you're running C++ code, you have raw pointers. It's very easy to compromise those raw pointers. And once you compromise those raw pointers, you can, and there's also system calls that you can, whatever. So so basically anything in memory can potentially be easily compromised because with these raw pointers, once you somehow find a vulnerability that lets you to access these pointers, you can hack these pointers to point anywhere and read and write to anything. And if your memory is in danger, that means your program code can be changed. And then anything in your stack can be changed. And then if anything in your stack can be changed, that means the instruction pointers and registers can be changed. And then just assuming the whole program is compromised, that means you can make any sort of system call you want to make destructive changes to your system, like network I/O or file I/O or whatnot. And of course, on a modern operating system, we have a little bit more protection than that. So yes, because you're running C++ code, just the fundamental property of C++ is you have raw pointers, so anything in memory can still be compromised. But you can protect your program code a little bit by making it read-only, so that you can't sort of modify existing code, and you can label it so you can only run code that was that you yourself loaded. So you can't create new code to load. But even then, your stack is still pretty vulnerable, and that means your instruction pointer is vulnerable. So even though you can't create new code, you can still sort of trick a program to run code unexpectedly or with different parameters and stuff. So that's a pretty big vulnerability. So you still want to protect your system calls a bit. So in a modern OS, you can add some sort of access control or address space randomization to sort of protect, to prevent your renegade process from being able to write files that shouldn't or things like that. So if we look at WebAssembly, in WebAssembly, you have raw pointers because it's C++ code. So everything in memory can be compromised. And that includes the C and C++ stack. But your program code actually exists outside of memory because it's not in memory. And then you can access your program code through limited instructions, but those instructions only allow you to call functions or return from functions. You can't get a memory reference to those two functions to modify them. Similarly, the sandbox stack, there are instructions for, in order to access the stack, you either call a function or return from a function, or you can read a local variable or write to a local variable, but you can't get any memory references to anything on the sandbox stack. So by hacking your memory pointers, you can't get at that sandbox stack, so that's also protected. And then if your sandbox stack and program code is protected, that means your instruction pointer is protected as well. So yeah, you can see WebAssembly has more protection than just a regular operating system process. And then on top of that, let's say you're just running malicious code that you downloaded off the internet. You're limited in what sort of destructive changes you can make because, like I said, WebAssembly is only for computation. So you can only call out to the JavaScript functions that you explicitly import. And then even then, because JavaScript is itself sandboxed, you sort of have to break out of two sandboxes to do anything malicious. And just for comparison's sake, we can look at Java. So Java doesn't have this memory pointers. So they just have an object heap where you have different objects. And these objects are fairly protected in that you can't manufacture pointers to just get to any object. You have to follow memory references around. And even if you have a memory reference to an object, you can only access its fields in safe ways. And then your program code is safe, just like WebAssembly. And then your stack and instruction pointers are also safe. And then if you want to do sort of more permanent changes like file I/O and network I/O, I guess Java does have a security manager that you can use to sort of protect yourself a little bit. But I guess, I don't know, most people don't really configure that all that well, or it's too exposed or not that exposed.
It's getting deprecated.
Oh, OK. So yeah, it's you can say there's more protection than WebAssembly or less, depending on which part you want to protect. Containers. So these are just other ways of sandboxing things. Right. So just as a general idea, if you're comparing WebAssembly and Java, the main difference between WebAssembly and Java is that WebAssembly is for low-level languages like C++. That's what it was designed for. Because it's designed for running C++ code, you have access to raw pointers. And just having access to raw pointers means it's less secure than Java. But it is faster in some sense because you have less typing, right? You can just access whatever you want in memory. You don't have to check if it's safe. But despite this sort of less security in the Java, it is more secure than other sandboxing things like containers or OS virtualization or something like that. So I guess now that we have a general idea of WebAssembly, let's see how we can use it from Java. So this is the sort of base pipeline tool chain you can use for running WebAssembly code. So basically, all the tool chains are based on LLVM right now. So you take your C++ code, you stuff it into LLVM to compile it. It will output pure WebAssembly, and then you can run that in whatever WebAssembly virtual machine you want. The problem here with this tool chain is that LLVM outputs pure WebAssembly. And like I said, WebAssembly only does computation. So if you want to do anything useful, like anything that interacts with the user, this sort of tool chain is not useful because you can only do computation with it. So if you want to do something in the browser, they have this other tool chain. So they have this compiler called mscripten. So basically, it's again based on LLVM, but it's designed as a GCC replacement. So if you have some makefiles that use GCC, you can just replace your GCC with mscripten as the compiler and just compile your code that way. And mscripten outputs a sort of mix of WebAssembly and Java. So it has Java to initialize the WebAssembly, and the WebAssembly will often call into into JavaScript to just interact with the user or whatever functions you want to import and stuff like that. And because this output of mscripten is a mix of WebAssembly and JavaScript, you basically need a browser to run it because you need a JavaScript engine. So neither of these is that good for use on the server because often you want to do more than computation, but you don't want to lug around a JavaScript engine. So they have this other tool chain for running things on the server. And what they've done is they've created this library known as WASI. So it's basically a bunch of, I guess, system calls that you can call out from WebAssembly to do file I/O and network I/O and stuff. And basically, what you do is you download the WASI SDK, which is, again, another version of LLVM. You feed your C++ code into that, and would output pure WebAssembly, but with dependencies on this WASI library. And then they have different virtual machines, such as Wasmtime and Wasmer. And these virtual machines contain the WASI library. So if you run your WebAssembly code on these virtual machines that contain the WASI library, your WebAssembly code can then call out to WASI to do file I/O and network I/O and stuff. And I guess since we're Java programmers, I'll mainly look at this sort of server toolchain because, yeah, we want to do more than computation, but we don't want a JavaScript engine. So yeah, so I guess now that we can see we can run WebAssembly code on the server, why do people want to run WebAssembly code on the server? I looked at some blogs, and it's not really too clear why. I guess the main reason people give is that they have some code that they need the performance of C++ for some reason, but they don't want the security vulnerabilities of C++. So obviously, C++ is a little insecure, but you don't want to let people compromise their whole server in case they break out of the compromise their C++ code somehow. So I guess if you have some AI code or something written in C++, WebAssembly is one way you can run that securely. And then another reason they give is they claim that WebAssembly has fast startup and teardown, which makes it good for serverless functions. And it's not really clear why they say this, but I guess compared to other sandboxing things, I guess WebAssembly has less code that you have to restart, since you don't have to restart the operating system or reload runtime libraries. It's just your WebAssembly code that you have to restart. OK, so let's say, you want to run WebAssembly on the server, and you want to do it with Java. The first issue you encounter is that the main server runtimes for WebAssembly don't support Java. It's not really clear why. Like, they support things like Go and C# and Python. They never really justify why they don't support Java, except that they don't. But fortunately, there are various alternatives available. So there are people have made their own hobby Java bindings for Wasmtime. And then also there's also GraalVM, which supports all sorts of languages, and they threw in WebAssembly support more recently as well. So just to give you an example of actually how you would get WebAssembly code running on Java. So here we have some C++ code, and if you want to get it running using WebAssembly, so yeah, just to look at this WebAssembly code, it's just a hello function that prints hello world, and then here I'm exporting that hello function as hello, so that you can it's available from outside the program. So basically, if you want to compile it, you would get this WASI SDK, and CLang is the C compiler for LLVM. So you'd compile it with CLang, you'd specify, you'd tell it to use the WASI libraries. And then you'd say, this is the file you want to compile, and you can output the WebAssembly into some a.out file.
Is it statically linked to the a.out?
Yeah, it's all, well, like the WASI libraries, it has a runtime dependency on that, so you need that in your virtual machine.
Okay, so if a.out includes what, do I have to run the VM before I run a.out, or can I just run it by itself?
No, you'd have to run it in a WebAssembly VM.
Okay.
Yeah.
That attribute export name, is that like a normal C++ thing, or is that specific for WASI?
Yeah, I think it's a CLang. It's a LLVM thing. So if we then want to call that from Java, so here you can, this is sort of a Maven package import that has some hobbyist bindings to Wasmtime. And then here's just some code to run it. So basically it starts up the WASI library. It starts up your WebAssembly. It loads the WebAssembly code from a.out. It links everything together. And then you get your hello function and you run it. So yeah, the details aren't that interesting, but this is the general idea. Yeah.
And how fast is this? If you just run this code, like this whole block?
Yeah, I'm not sure actually. Like it's a hobbyist binding, so they don't. It's not. I don't think they spent a lot of time optimizing it or anything like that. So just to give you an idea of what sort of performance you can expect from WebAssembly, I created a little performance benchmark. So I took Box2D. So if you aren't familiar with it, it's a physics library for games. And it's normally written in C++, but they've ported it to Java and JavaScript and a bunch of other languages. So this means we can compare the performance across different languages with it. So basically, in this benchmark, I took a bunch of circles and squares, and I dropped them from the screen and simulated it for a while and measured how long it took. So the lower the number, the better. So on the left, you can see your Java performance. And then on the right, you can see what happens if you just run it as normal Intel AMD 64 GCC code. So you can see the C++ code is faster than Java. So yeah, you might want to get that performance somehow in your Java code, and you might want to do that using WebAssembly. So in the two middle bars, I've taken that code and compiled it to WebAssembly, and then ran that WebAssembly code on two different virtual machines. So the second one is wasm time, and the third one is running it in Chrome. And you can see that with WebAssembly, the performance gets pretty close to native code, but it's there's still a bit of a gap, just because there's some overhead with WebAssembly, and they probably aren't as optimized as the full GCC compiler. Okay, so yeah, I guess you can see that WebAssembly gets you most of the way to C++ to native. Okay, so you can see you can combine WebAssembly and Java. So I guess why would you want to do that? So I guess one reason you might want to do that is if you have a C library and you want to use it in your application, but you don't entirely trust that C library, because if it gets compromised somehow, your whole application gets compromised. So if you use WebAssembly, you can run that C library sandboxed and get most of the performance of the C library, but with some protection. And similarly, if you have an application with plugins, you can sandbox plugins that way too. And another thing that might happen is if you use JNI a lot, so if you have C++ code and you sort of include it with your Java application, you'll find it's a bit of a pain, because you have to compile that C++ code for every architecture you want. So that's Windows on ARM, Windows on 64-bit, Windows 32-bit, Linux, ARM, Linux, and then Macintosh and whatever. And it's a real pain compiling everything, and every compiler is a little bit different and whatever. It gets to be a big mess. But with WebAssembly, you just compile the code once to WebAssembly, and then you can run that on whatever architecture happens to have a WebAssembly runtime on it. So yeah, in a way, it's more portable than the C++. It's easier to do. And yeah, so I guess I talked about how to use WebAssembly from Java. So we looked at how to run C++ and Rust code on WebAssembly. And I guess that begs the question of, like, how do you run Java on WebAssembly? And if you can run Java on WebAssembly, can we run all these dynamic languages on WebAssembly? And if we can run all these languages, why don't we just run everything on WebAssembly? And I guess theoretically you can, of course, right? Because C++, it's a Turing-complete language. So technically, in some sense, everything can be compiled to C++ at some level, and then you can run that on WebAssembly. And I guess like Python, they sort of do that. I guess they just give you a Python interpreter. But I guess the issue is, all these languages, they all have features that aren't in C++. And since WebAssembly was designed for C++, it's missing in WebAssembly as well. And so to get the maximum performance out of these other languages, you need explicit support for these features. So especially for something like Java, the garbage collection is important. Dynamic dispatch, a lot of Java gets a lot of its performance from just-in-time code optimization, so that which isn't in WebAssembly normally. And then one nuance with garbage collection is you also need it for JavaScript integration, because all the APIs in a browser are in JavaScript, and so in order to access those APIs, you need to have memory references to JavaScript objects. And if you don't have a garbage collector on your side, you can't safely have references to JavaScript objects. meaning you can't have a good integration with JavaScript. But even without these features, supports in WebAssembly, like I said, you can sort of hack everything to run on WebAssembly at some level. So you could use TVM to run Java on core WebAssembly. But even the TVM guys will say, like, yeah, this is sort of a bad idea. Like, we have to include a whole garbage collector in your code in order to garbage collect your code. And if you can't interact with JavaScript, then like, what's the point of doing this, right? It's a bit of a mess. But people know that core WebAssembly is missing a lot of features, so they have made an extension. It's not in Safari yet, but it is in Chrome, and I think it's in Firefox. And it's WASM-GC. So basically, this adds garbage collection to WebAssembly, and it adds other things. It also adds a basic structural type system. So I guess to run garbage collected code quickly, I guess you need types in order to access fields and stuff without having to keep checking things. And then they also let you store data in pointers, which is also used by some garbage collected languages. So the basic idea is you take your WebAssembly model, and then you just cram in an object heap in the middle. And your local variables can access these objects. Your objects can have references to each other. And your garbage collected objects can also have references to JavaScript objects. And I think JavaScript objects can also hold references to objects in your object heap. So if you look on your left side, it's like basically the Java model. But then if you leave out the object heap, it's the WebAssembly model. So they sort of smush the C++ and Java stuff together. But I guess that's the best you can expect, really. So one issue is WebAssembly GC was designed for Flutter, because someone has to champion this idea and to make all the compilers and to test everything. And I guess it was done by Google. But the Flutter people, they worked on Java and JavaScript in the past. So just because it's designed for Flutter, there's a reasonable hope that it should work for Java. And in fact, Google, they did make a proof of concept compiler of Java to WASM-GC. So they took their J2CL Java to JavaScript compiler, and they made it output WebAssembly. And it works, but there's like no documentation. There's like, it's not on their roadmap. Like no one knows. So like you can get it to work, but no one knows if it's going to be supported in the future or anything like that. So if you do need something like a higher level dynamic language to WASM-GC, for now it might be better to look at Kotlin, because Kotlin does have a Kotlin to WASM-GC compiler, and it's on their roadmap. So they do intend to productionize it so that you can use it. So to give you an idea of the performance, so I guess this is that Box2D benchmark again running on Java. And I use J2CL to compile it to JavaScript. And you can see that, Java is faster than JavaScript. We sort of all knew that. So obviously, if you're running JavaScript code, you want something faster than JavaScript. So if you were to take your JavaScript code, Java code and compile it to WebAssembly GC and run that in Chrome, you can see that, yes, the WebAssembly GC is much faster than the JavaScript, but it's not quite as fast as normal pure Java running in a JVM. But I guess it's still early on. So I guess over time, this performance gap might narrow as the WASM-GC matures a bit and as the compilers to WASM-GC mature a bit. But if you need the best performance, it's probably better to go with C++ and compile it to WebAssembly and run that in a browser. If we can run Java in WebAssembly, do we still need the JVM? And I guess yes, because WASM-GC, it's designed for the browser, so it's not clear if it can scale to the same way the JVM can. And of course, since the JVM is made purely for Java, it will probably always be faster. And you have to ship your runtime libraries with your WebAssembly code, so that can load up your code as well, things like that. So I guess these are all the things we've covered so far. I guess we can just look at conclusions and speculate a bit about the future. So I guess you can see WebAssembly, there's a lot of promise in it. It's pretty powerful, but it has huge gaps. Like I said, there's no real Java to WebAssembly compiler and things like that. So, but it's evolving quickly, so hopefully this will sort of get cleaned up in the future. So in terms of using WebAssembly for the web, I guess, yeah, WebAssembly, yeah, it does have some staying power for use on the web, just because you need it for performance. Because if you need sort of high computation, high performance computing in the web browser, you have no choice, right? You have to go C++ to WebAssembly and run in a browser. You can't do that with JavaScript. But in terms of whether it will replace JavaScript, I don't know. Like right now, the toolchain is pretty messy. And I think over time, they might be able to refine it so that it becomes similar to TypeScript, where you can like just use some Node.js thing and compile things. But that's still a ways away. And even then, it's not clear who's going to make all this tooling. Because it costs money to make all these compilers, and I'm not sure like who's going to support it. In terms of WebAssembly for the cloud, people keep saying like, okay, it gives you performance with security and fast startup, but it's not really clear whether you want to give up security for like this performance and stuff, and whether if the fast startup is as fast as they claim it is. But they do claim this future benefit of polyglot programming. So they say, oh, you can mix your Python and your C# and all that and run it all in the same virtual machine. And they say this will be some magical feature. But even then, I guess, just because you can get different languages running on the same VM, it doesn't mean they're compatible, right? They still have different data formats. So you're still going to have to go through these messy interface APIs to sort of get them to work together. And it's not clear if people actually want to do it, because if you look at something like the JVM, you can mix Kotlin and Java code or Scala and Java code together. But like they keep discouraging you from doing that, right? They say if you're going to program in Scala, just code entirely in Scala. And like the Java is available, but it's not something people actually want to do. And so it's not clear whether mixing Python and C# or in Java in one VM is something that people will actually want to do. And of course, there's the issue of who's going to maintain this tooling for compiling to WebAssembly again. And one interesting thing is, right now with WasmGC, right, it has a garbage collector and type system and stuff like that. And all of this infrastructure is already in the JVM. So it's very easy for them to extend the JVM to support WebAssembly. And then you can get this sort of deep integration between WebAssembly and Java code, because they can hold references to objects from different languages and stuff like that. And in fact, if you look at GraalVM and Eclipse OMR, they have included WebAssembly in those VMs. So yeah, this might be some direction that might happen. In fact, I guess GraalVM might have a talk in January where they talk about GraalWasm and other things. And then finally, I guess one possible interesting use of WebAssembly is as a universal intermediate representation. So basically, WebAssembly has one strong core toolchain, because if you need high-performance computing in the browser, WebAssembly is the way to do it. So people maintains the tooling for that. And I guess once you have one strong toolchain, you can piggyback off of it. Like if you want to run other things in the browser, you might as well output WebAssembly. And then once you have all these languages outputting to WebAssembly, you might as well create other backends to run WebAssembly in other places. And then you might be able to mix things together where you can run sort of C# on the mainframe through WebAssembly, or Java on the iPhone through WebAssembly, or something like that. So this might be something that might come in the future, I guess, as WebAssembly matures. So yeah, I guess that's the talk. Any questions? Yeah?
Yeah, I want to go back to the first slide where you had the stack. So what's the difference between the sandbox stack and the other one, the regular stack?
So I guess the idea is the sandbox stack is the only one that's secure.
So if, like, for example, a C code returns a pointer, you can't do reference it in the sandbox class.
So the compiler will check if you try to get memory pointers to things on the stack, it will store them in the C++ stack.
Okay.
But otherwise, it'll store them in the sandbox stack because it's more secure that way.